never turned Excel on before. If you have, you're ahead of the curve, obviously. But if you haven't, I've set the assignments up assuming that you never have. So what I've done here is I've randomly generated some values between 0 and 20. Between 0 and 20. So right now, there are no zeros. Let me turn this off. Wish I could make it. Oh, God. Is that okay? For temporarily anyway? We can see the numbers on the screen much better this way.
Yeah.
Okay, good. So right now there are no zeros, there's 1 1, there are no 2s, there are 2 3s, there are 6 4s, 19 5s, and so forth, and so forth. It generates kind of a nice little bell curve. Every time I press the F9 button, I'll get new values. These are all based off of random numbers that Excel is generating. It's one of the neatest functions that spreadsheets can do, called Monte Carlo simulations. More on this to come. More on this to come throughout the course. I'll have you messing with these from time to time. It generates random numbers so you can see if any patterns arise. Because we saw it in one set of random numbers, the number of keys you had in your pocket, which essentially is somewhat random. I mean, it's somewhat random, not for you personally. You probably have the same number of keys in your pocket every day. But people that walk into this room taking my class, it's sort of random, to some degree, how many keys you have in your pocket. So this is just essentially taking, I think I have 1,000 data points altogether. I'm pretty sure there are 1,000 different random numbers all being plotted in this screen. So every time I press F9, I get 1,000 new random numbers, and they're falling into that curve. See how that curve is predominantly bellish shaped? But it's definitely fluctuating each time I press it. Okay, it's fluctuating, but it's predominantly bellish shaped. So right now, the raw data has an average of 10. So all these data points, if you add up all these data points and average them weightedly, so if you did 0 times 0 plus 1 times 0 plus 2 times 2 plus 3 times 1 plus 4, just like we did in class, yes? Plus 4 times 4 plus 5 times 20 plus 6 times 26, all the way across, the average becomes 10. Divided by 1,000, the average becomes 10. With me so far? So essentially that's just like an old school average, you know? 2 plus 2 plus 3 plus 4 plus 4 plus 4 plus 4 plus 5 plus 5 plus 5 plus 5 divided by 1,000. That gets annoying quickly. So what I did behind it was I grouped them together. So right now, if you look between 0 and 2, there are 2 data points altogether. There's no zeros, no 1s, and 2 2s, which means altogether there are 2 numbers in this range. Between 3, 4, and 5, there are 25 because there is 1, 3, 4, 4s, and 25s. So what I've done in the back there in red is I've grouped them in sets of 3. Instead of sets of 1 like they are up front, they're in sets of 3. 0 to 2, 3 to 5, 7 to 9, 10 to 12, and so forth and so on and so forth and so on all the way along. Fair enough? Now, you'll notice that they update as well every time I press F9. F9 is like rolling a set of dice. But you'll notice also that these 3 add up to that one red number in the back. So 3, 10, and 25 add up to 38. 6, 7, and 8, so these values here add up to 23. 9, 10, and 11, these guys here add up to that one there. What I've got up there, the grouped data average, is how you would have to do the average if you removed the blue curve and lost all that precision of having the raw data. So in other words, right now, you would call this category a frequency of 1, but you would assume it has a numerical value of 1. Because if all you have is the group 0, 1, and 2, you can't say, oh, it's a 2. You assume it's in the middle of each of the groups, yes? You assume it's in the middle. This group here, that has 38 in it, that spans the distance between 3 and 5. So what are you going to say they all are? You're going to say they all 4. Now notice, because we have the blue in front of us, notice that 4 is actually not the majority of the data, is it? 5 is. So that's going to be an incorrect, that's going to be off a little bit, isn't it? Keep that in the back of your mind. Keep that in the back of your mind. How about 6 through 8? We're going to say they're all 7s. But again, that's also a bit of an offness, isn't it? Now remember, you're not going to see the offness because you don't have the raw data when data is grouped. I'm setting up a bit of a hypothetical here where I have the raw data and I'm grouping it behind it. So, hypothetical. 9, 10, and 11, we're going to say they're all 10, which is actually good in this case because 10 generally is the one that happens the most. But now look what happens on the back side. 12, 13, 14. We're going to say they're all 13. Again, that's wrong because there are more 12s. But do you see what we did here? We're actually overestimating the values in this bar, but over here we were doing what? We were underestimating, weren't we? We were underestimating here, we're overestimating. How about this bar right here? We're going to say 15, 16, and 17 goes 16, which means we're actually overestimating again, but that's going to counter this guy over here, which is an underestimate. So you see what happens over time? Your individual bars are going to be all off. They're either going to be most likely overestimates or underestimates. But if you overestimate in one, on average, you're going to underestimate somewhere else to make up for it. Now don't trust me on this. Call BS on it right now. That wasn't very loud. BS? I'll take that. Don't trust me. Look at the replication. Watch the grouped data average as we keep simulating data. What do you notice about that average, friends?
It swings really close.
It rounds to 10 almost every single time. Matter of fact, it doesn't get very far away from 10. Let's see if we can get it for you. 10.0, 9.8, and that rounds to 9.9. We're off by a tenth there. 10.1, 9.9, 10, 10, 10. So what's happening is, on average, this is called the law of large numbers. Don't memorize this. The law of large numbers kicks in when you start replicating on average over time. You're sick of hearing it, I'm sure, from 105. On average over time. The individual data, if you properly group them, will be approached by the grouped data. On average over time, if you do it correctly. If you do it correctly. It emphasizes the importance of replicating studies, first of all. More on that in 244. But it also puts your mind at ease when you're dealing with group data that you can actually pull meaningful numbers from the data. Now, eventually, this is definitely bell-shaped data. I ran out of time. I was going to make some more different kinds of data, like goofy shapes, like W-shaped data and left-right data, but I didn't get around to that. Well, eventually we will. If I can get it done before the end of the term, which probably won't happen, I'll bring it back to class and show you then, to show you that it still works that way too. But this is why, this is one example why grouping data is fine. You can still pull meaningful numbers from that data. Fair? Okay, good. Thank you, friends. Thank you, friends. Let's shut that down. Fire this guy back up. Let's go to here. So there's our historical data. Feel good. Put this back on. Sorry. Oh, sorry. We got our stuff on the board. It gets too hard to see. All right. So here.